This book is Thomas's Calculus, 13th edition. From this file, you can find Chapter 11, Parametric Equations and Polar Coordinates. In this chapter, Section 2, Calculus with Parametric Curve. If you scroll down, you can learn how to evaluate derivatives and integrals when using parametric curve. For example, x is a function of t, y is a function of t. We can evaluate area bounded by this curve. I tried all the examples and solved numerically. For example, this is line length of these parametric equations. Because we defined derivative, also integration, I could easily compute such integrals. If you scroll down, you can find more examples. All such things solved very easily. Even revolution about x-axis, we can compute area of surface of revolution for parameterized curve. Because we implemented derivatives, also integrals, solving such problem is a piece of cake. In exercise 11.2, implicitly defined parameterization, I tried problem 15. So, we are given two equations. This equation contains variable x and t. This equation contains variable y and t. We want to evaluate the slope of this curve. When x is defined as a function of t, when y is defined as a function of g of t. Solving problem 15 was of no problem. But when I tried problem 17, it caused serious problem. But I successfully solved this problem too. By solving this problem, I made very important correction to my derivative algorithm. Without further ado, let's get started. Open up Visual Studio Code, CPP 17, 20, 23 parallel. Select empty space. Click this button, 162. I will name it Implicitly Defined Parameterization. Click this button, param.cpp. Hit enter. Ctrl B. I will copy this text. In this episode, we'll be using std isnan, this function. My name is Thomas Kim. First edit. Today is December 13th, 2022. If you haven't watched my previous videos listed here, you probably may not understand. Include CPG, SED, extension. Include CPG, calculus, namespace, CNA, CPG, numerical analysis, namespace, CPT, CPG, types are well arranged. I got this example from Thomas's Calculus, 13th edition, Chapter 12, Exercise 11.2, page 669. 669. Implicitly defined parameterization. I will title this function Implicit Parametric Problem 15. Here, xt means function x over t. We will define this x cubed 2 times t square. We need auto t auto x semicolon return paste x times x times x plus 2 times t times t. It should be like this. Okay, this is implicit function auto yt. So this is yt. We are defining this function auto t auto y semicolon return 2 times y times y times y 3 times t times t negative 4. So this is implicit function. Now we defined yt and xt. I will fix like this. Now auto we evaluate dx over dt. Okay, this is partial derivative. CNA implicit derivative. We have to pass the position x. The position of t is 0. The position of x is 1. We have to pass the position of 1 because we want to evaluate dx over dt. We pass xt. Xt is this function. Then we have to pass the value of t. The value of t is 2.0. Sadly, we have to solve this equation about x. If we substitute 2 for t, then x is 1. So we have to provide 1.0. I implemented Newton's method for such purpose. I will explain Newton's method in near future session. SED, Cout, dx over dt, dx over dt, CPG, and there. Now copy, paste. We evaluate dy over dt. We have to pass yt. The value of t is 2, the same. If we substitute the value 2 for t in this equation, then we have 2.0. I will explain how to solve such problem in near future using Newton's method. With this, I will put enter. STD, Cout, you can say dy over dx equals dy over dt over dx over dt. This is our result. Then dy over dt over dx over dt. CPG, and there. I referred to the answer sheet. The answer sheet says SED, Cout, exact answer is negative 3.0 over 16.0. CPG and L. Okay, we will call this function int main, copy this function name, paste it here. We can use any compiler. Let's try with Microsoft compiler. 162 implicitly defined parameterized initializations. Sorry, I made typo. I have to remove E. This is typo. No problem. CL, EHSC, SED, C++20, param.cpp, fe, m.exe, hit enter. CLSM. So we computed successfully the exact answer and our numerical calculation matches. Now let's move on to problem 17. This problem is very advanced. Scroll up. I will copy the function name, paste it here. Now it is problem 17. Copy, paste it here, disable it. In the same manner, auto xt, auto t, auto x. So we are defining this function. Here, x plus 2 times x to the power 3 over 2. Now I shift t square and t to the left hand side. It should be negative t square negative t 0. We will use this function. Return paste semicolon here, semicolon here. Of course, it should be SED power x over 3.0, 2.0. This is t times t. Now we define this function. Auto yt, auto t, auto x. This is y times SED square root t plus 1 plus 2 times t square root y. Okay, copy, paste it here, return. It should be negative 4, semicolon. I will give a line break here. Don't miss semicolon. Auto dx over dt CNA implicit derivative. We pass the position of x 1, then xt. In this problem, t is 0. The value of t is 0.0. Okay. If we substitute 0 for t, then x is also 0. So 0.0. SED cout dx over dt dx over dt cpg and there auto dy over dt. I will simply copy paste. Now this is yt. this value represent the value for t. If we substitute 0 for t, this term becomes 0, and t plus 1 is 1. Because t is 0, so y is 4. So this should be 4.0. I will copy, paste. This is dy over dt, dy over dt. STD, I have to fix the typo STD. C out dy dx equals, this is dy over dt over dx over dt. I will copy, paste it here. CPG, and there. I will put carriage return and L. STD, C out. Exact answer is negative 6.0 CPG and L. You can refer to the answer sheet. Answer to odd numbered answer sheet. Okay, I will go back. It is in page 669. Exercise 11 to problem 17. Now we copy and paste this function in the function main. We build again, hit enter. 83. It should be y. We build again. It is built successfully. CLS M. Wow. We have dx dt, not a number. So our evaluation failed. How can we handle such problem? If we want to handle such nasty problem, we have to understand underlying mathematics, also our algorithm. Implicit derivative. This function is defined. CPG calculus. Here, in this file, implicit derivative eventually calls generic gradient. This generic gradient, go to definition, calls partial derivative. This partial derivative calls, I will select this one. This function eventually calls 5-point stencil. This 5-point stencil again is defined here. CPG calculus. In 5-point stencil, in case of first order derivative, we call function f at x plus h, at x minus h, at x plus 2h, at x minus 2h, so 1 point, 2 point, 3 point, 4 point. In case of even ordered derivative or second order derivative, our function calls fx once, 2, 3, 4, 5. Basically, our algorithm uses 1 point, 2 point, 3 point, 4 point, 5 point in case of even order derivative. That's why we call 5-point stencil algorithm. 5-point stencil algorithm is explained in this document. Control click in the 5-point stencil algorithm. This point represents the value of x. To my eyes, it looks red color. This blue represents other points with respect to x. This distance is h. From red point, this distance is blue 2h plus 2h. This point is minus 1h. This point is minus 2h from the value of x. So, in case of first order derivative, we call fx 4 times x plus 2h, x plus h, x minus h, x minus 2h. In case of even ordered derivative, we call function f 5 times at x plus 2h, at x plus 1h, at fx, at x minus h, at x minus 2h. So 1, 2, 3, 4, 5. We are using 5 points with the center x. We have to understand 5-point stencil algorithm first. The problem occurs in this term. In our source code, we use power x 3.0 over 2.0. This x should be greater than 0 or equal to 0. Okay? If this function to be evaluated successful, x should be greater than 0 or equal to 0. X should be greater than or equal to 0. So, to address such problem, I will create a function here. Template. Type name type. Type name arg type. Void handle non-inf. Type f arg type x or n arg type h. Please understand that I used L-value reference for x, also L-value reference for h. Please understand this implementation is far from being perfect. I will give perfect implementation later, or by the time you acquire this file, you can find perfect implementation. Here, auto f neg h f x minus n times h. Copy, paste. This is positive h. We plus if SED is none. We are testing if this is not a value, or SED is inf. If this is infinity, then we modify. If this function returns not a value or infinity, then we redefine SED numeric limits by passing ARG type epsilon, such as very small number 100. Because epsilon itself is very small number, it is still very small number. Then we shift n times h. Okay, in this case I will explain. If our function at this point, okay, this point is x minus n times h, because h is always positive. This point represents this point on the leftmost side point. So we make h very small and we shift to the right, okay, to make it positive, to make x greater than singular point. Else, if we copy, paste it here, now it is positive h. Positive h. I say leftmost evaluation of f. This is rightmost evaluation of f. So in this case, we still make h very small, but we subtract. What it means is that if this point returns not a number or infinity, then we move the whole points to the left. Okay, this is what it says. Now with this, I copy, scroll down in the 5-point stencil. This is first order derivative. We pass f, then x, then n. N is 2h, so we pass 2, then h. Please understand, we modify the value of x and the value of h. In this algorithm, we modify the value of h. We make h very small. Also, we move the value x. We used L-value reference. L-value reference. That means in this function, when we call handle non-infinity, this h changes, so it should be fixed like this. I have to apply this function here too for second order case. Also delete this, copy, paste it here, also remove context per. In the same manner, this is fourth order, delete this. 5-point stencil. In case of 5-point stencil, I defined up to order 4. What about order 5? Then I call 7-point stencil. The reason I implemented this way is for performance. In case of 5-point stencil, we use 5 points lower than fourth order. Our algorithm is accurate enough. But when the order of derivative is higher than fourth order, accuracy significantly degraded. So we elevate to 7-point stencil. The same goes true if 7-point stencil algorithm. Go to definition. Here 7-point stencil algorithm should also be fixed. If you scroll down, 7-point stencil algorithm supports up to order 6. Higher than order 6, I use 9-point stencil algorithm. 9-point stencil algorithm supports up to 8th order derivative. The reason I implemented this way is for accuracy as well as performance. With this, we can rebuild CLSM. Wow! dx dt is 1, dy dt is negative 6. This is our numerical computation. This is exact answer in this book. This way, we can solve such nasty problem. Please understand, as I said, handle non-infinitive. This function is not yet perfect, but I want to give you how to fix the error. I will make it perfect by the time you get the source code of this file.